welcome to Easy BTech, your guide for BTech and beyond. In this channel, you can learn the subject very easily. My name is G. Sampath. I am going to explain the subject VLSI design. Today, we are going to discuss the topic counters. It is data path subsystem design. It is a subsystem design. Okay, counters are used in different applications, right? So, what is a counter? So, counters. So, counters are counting the number of clock pulses. Counters are counting counting number of clock pulses. Number of clock pulses that we are applying. Okay, counting the number of clock pulses. Okay, number of clock pulses. Okay, so applications are counters are designed by counters are designed by JK flip flop in toggle state. Okay, JK flip flop in toggle state. Okay, toggle state or T flip flop. Okay, T flip flop. Applications are counters are used in applications are used in frequency counter, also RF counter, radio frequency counter. Frequency counter, another one, digital clock, A to D converter, analog to digital converter, analog to digital converters, right? Converters. Okay, also used in time measurement, and any device, digital display, used in digital display. Okay, all digital displays are used by these counters. The number of clock pulses, counting the number of clock pulses, digital display. Okay, let us see this one. Counters are two types of counters. Okay, two types of counters. Okay, so one is asynchronous counter, second one is synchronous counter. Let us see. One is can say synchronous counter. Second one is synchronous counter. Second one is asynchronous counter. You can say first one you can take asynchronous and synchronous counter. Okay, synchronous and asynchronous counter. So mainly it will be ask you difference of asynchronous synchronous in examinations, important. Okay, so the first point is know each output as a clock to the each output each flip flop output, each output that is nothing but a flip flop as a clock to the next stage, as a clock to the next stage, as a clock to the next stage. Okay, and here no such type connection. Okay, no such type connection in this. So then output is not as a clock to the next flip flop. So no such type connection, no such type connection. Okay, and the second one is no simultaneous clock. Okay, simultaneous clock, no simultaneous clock, no simultaneous clock. Only first clock pulse is applied to the first flip flop. Each output has a clock to the second stage, and here simultaneous clock is applied. Simultaneous, okay, simultaneous clock applied. Okay, clock applied in this synchronous counter. Okay, right. And the third one, and the third one. So time delay more should wait for the second flip flop. Wait for the output of first flip flop as a clock. So it will take time delay. Okay, time delay more. Time delay more. So there is no time delay. No time delay. No need to wait for the clock. So it is a simultaneous clock is applied. No time delay. No time delay happened in this synchronous counter. And the fourth one, and the fourth one, we can say it is easy design. We can say it is easy design. Okay, it is easy design. And the fourth one here, somewhat complex design. Okay, it is a complex design. It is a complex design. Okay, let us see the cost oriented. So low cost. It is low cost design, and this is a high cost design. This is a high cost design. Okay, high cost design. So this is a differences between asynchronous counter and synchronous counter. Okay, so asynchronous, each flip flop output has a clock to the next stage. No such type of connection. No simultaneous clock. Simultaneous clock. Time delay is more. Should wait for the output of first flip flop as a clock to the next stage. So no need to wait it. So no time delay. Right. Easy to design. So there is a complex design. It is a low cost design. Okay, and it is a somewhat high cost design. So these are the differences between asynchronous and synchronous counter. Let us design the 3-bit asynchronous counter, then design the synchronous counter. Okay, 3-bit or 4-bit, 3-bit asynchronous counter, asynchronous counter. Okay, 3-bit asynchronous counter. So for easy, then you can see this 3-bit or 4-bit in the examination. We can increase one more flip flop. Nothing is there. Okay. So asynchronous counter. Let us see the diagram. We can take the flip flop. Let us take the 3 flip flops over here. 3 flip flops. JK flip flops. Okay. 3 JK flip flops. Okay. Designed by flip flop it is. Okay. So and 3 inputs. Sorry. 2 inputs are here. 2 inputs are here, which are connected to the high signal, which are connected to this high signal. Okay, and each output as a clock to the next level state. Okay, each output as a clock to the next level state. Okay, then the first clock pulse is applied to the then first flip flop. Okay, so this is flip flop 0, flip flop 1, flip flop 2. Okay, it is a JK flip flop. JK. Okay, Q complement. Okay, Q complement. So it is JK. Okay, Q complement. Okay, so which are connected to the high. The high path is connected here. Okay, high path. Logic 1 or 5 volts or 5 volts. Okay, input we are applying a clock signal. Input we are applying a clock signal. The first clock pulse is applied. Then each output, first clock pulse is applied to the first flip flop. But second stage, the FF1. Okay, the second stage, output of the first flip flop as a clock to the next. Okay, as a clock to this one, as a clock to active low. Okay, as a clock to the next state. Okay, so these are the three flip flops designed by 3-bit counter. So outputs are here. We can say Q naught, Q1 and Q2. Q naught, Q1 and Q2. So asynchronous counter. So counter, it is connected by flip-flops connection. Flip-flops connected in series. We can say it is seriously connected. Okay. So one flip-flop output goes to the another flip-flop. So it is a flip-flop design. Okay. As per the clock pulses, then the counter will start. Okay. Let's see the truth table. Okay. Let's see the truth table, right? Clock pulse is applied q naught, q1 and q2, q naught, q1 and q2. Okay, q naught, q1 and q2 ma. Q naught, q1 and q2. So first clock pulse is applied, so 0. First clock pulse is applied, so counter is 0 0 0. Okay, and 0 initially clock pulse, then it will be 0 0 0, no change state. First clock pulse is applied 0 0 1. Okay, second clock pulse is applied 0 1 0. Okay, third clock pulse is applied 0 1 1. Right, fourth clock pulse is applied 1 0 0. Now the fifth clock pulse is applied 1 0 1. Right, sixth clock pulse is applied 1 1 0. Like seventh clock pulse is applied 1 1 1. So this is the output. Okay, so input is a clock, so this one is a output, counter output, counter input. Okay, counter input, clock pulse. Okay, clock pulse is applied. Okay, JK flip flop, you can see the previous, it is a JK flip flop. You can say JK flip flop. In JK flip flop we can take the two table 0 0 0 1 1 0 and 1 1. So Qn plus 1 next state. So it is operated in JK. It is 1 1. It is toggle state. Okay, toggle state. Or it will be 0 1. 0 1 is a set state. So it is reset state. Reset state. It is no change state. No change. Okay, or we can take it is a T flip flop. Okay, so this is a JK flip flop truth table. Okay, where 1 is connected, then it will be toggle. Okay, change it 0 to 1, 1 to 0. So otherwise both inputs are common. Both inputs are common and input is applied is a T flip flop. Okay, T flip flop. T flip flop. Okay, T flip flop truth table. Otherwise T flip flop truth table. So 1 is given. So Qn plus 1 next stage. 1 is given, it is toggle. 1 is given, 1 is connected, it is will be changed state 0 to 1, 1 to 0. When 0 is given, it will be no change state. Okay, it is Qn, no change state. 0, it will be no change state. Okay, so both inputs are common. It is a T flip flop. T flip flop. Okay, so as we see in this, so 0 0 0. First clock pulse is applied. So initially clock pulse is 0. It should be 0. When it will be 1, first clock pulse is applied. What happens? Then Q naught will be high. Q naught will be high. Remaining Q1 Q2 are no change state. Okay, so let me write here. Let me write here. Initial clock. Initial clock. In initial clock. Initial clock. Initial clock. So outputs are no change state. Outputs are no change state. Okay, no change state. So that is q naught, q1 and q2 equal to 0 0 0 ma. Okay, now clock 1, so clock 1 is applied. So clock 1 applied to the first flip flop, to the ff0. Okay, apply to the ff0. Okay, then q naught change it to, q naught change it to 1, q naught change it to 1. So q2, q1 q2, q1 q2 no change state, so q1 is equal to q2 is equal to 0. That is no change state, no change state ma, no change state. Okay, no change state. Okay, then clock 2 is applying, clock 2 is applying. So clock 2 is applying, what happens here? So clock 0, no change state, q0 q1 q2 are same state. Clock 1 is applied, you can see the truth table. So q0 change it to 1, q0 change it to 1. Okay, q0 change it to 1, remain q0 q1 q2 are no change state. Second clock pulse is applied, what happens? Before going to 1 to 0, it, before going to it going to 1 to 0, so it will be connected to the next flip flop as a clock, then it will be set to 1. Okay, then remaining q2 will be no change state. Okay, so clock 2 is applied to, clock 2 is applied, then before going q1 before change it to q1, change it to 1 to 0, 1 to 0. Okay, before going to, before change it to, okay, before change it to 1 to 0. So first it set, first it is connected to, it is connected to the flip flop 1, connected to, connected to ff1, ff1. Okay, ff1, ff1, q1 change it to, so connected to q1 as a clock, q1 as clock, q1 as a clock. So as a clock it is connected, then q1 is equal to 1, q1 is equal to 1. Okay, q1 is equal to 1 and q2 will be remains 0, no change state, no change. Okay, no change. So this may be happened continuously, this may be happened. So continuously this will be happened, continuously, continuously. So this function, continuously these functions happen. So these functions happen as per the clock, functions happened as per the clock. Okay, as per the clock, you see, as per the clock it will be happened ma. As per the clock it will be happened. Okay, you can see this one, it is a flip flop, jk flip flop, which is connected to high. So whenever it will be 1 1 means both are connected to 1, it will be change state, toggle state. 0 it will be 1, 1 2 it will be 0. Okay, initially all are 0 0 0, clock 0. Okay, so whenever it will be next count, for the next count clock 1 pulse is applied, so first it will be 1. Okay, 1, remaining q1 q2 no change state. Now clock 2, clock 2 before going to 0, first it is connected to this second flip flop, it will be set to this q1 1, then it will be 0 1 and 0 0 1 and 0 0 1 and 0. Okay, again next third clock pulse is applied, what happened? Jk inputs are connected to, jk inputs are connected to high. Okay, high level. Okay, high. Okay, so it is j and k, right? High. Now change state, now it is changed to 1. Okay, now what happens? Again it will be no change state, it will be no change state and this will be 0. So this may be happen continuously. Okay, now let us see the timing diagram. Okay, timing diagrams, timing diagram, timing diagram. Okay, timing diagram of 3 bit asynchronous counter, asynchronous counter, asynchronous counter. Okay, you can design this and timing diagram and truth table, these three must be explained in the examination. Okay, so as per the clock, okay, as per the clock which will be count. Okay, so clock signal, The clock signal we are taking here, let me take this one. Okay, clock 1, 2, 3, 4, each number. How many? 7. 0 to 7 clock pulses we are applying. Okay, 0 to 7 clock pulses we are applying here. Active low. Okay, leading, lagging edge. Okay, so let me take this one in this. Okay, 0, 1, 2, 3, 4, 5, 6, and 7. Okay, and 7. Right, and 7. Okay, now for the first one, Q naught. Q naught will be changes from here. Okay, changes from here. Right, changes from here. As the clock pulse is applied, it will be changed. Q naught. Okay, Q naught is changed. Now here also we can take this falling edge. Okay, now again it will be changed the falling time, falling edge of the pulse. Okay, right, this one. It is a Q naught, Q1, and another one is Q2 ma. Q2. Q2 will be taken from this. Okay, from here. Right, and Q2. Okay, so first clock pulse is applied. First clock pulse is applied. So let me take this 0, 1, 2, 3, 4, 5, 6, and 7. So initially 0, 0, 0. Now 0, second clock pulse 0, 0, 1. Okay, 0, 1, 0. Okay, 0, 1, 1. Okay, 1, 0, 0. 1, 0, 1, and 1, 1, 0, and 1, 1, 1. This is a timing diagram. This is the timing diagram of counters, asynchronous counter. So Q naught, Q1, Q2. So first count. So first count it will be 0. Okay, 0, and this will be 1, 2, 3. Count. This is a count. You can take the magnitude of 0, 0 means 0, 0, 0, 1, 2, 3. This is 4 and 5 and 6 and 7. So how many? It's a binary representation, means high, low, high, low. High it will be 1, low it will be 0. So counter value 0. Display count 0, 1, 2, 3. Again it will be converting a binary to a decimal. Okay, so it will be 0, 1, 2, 3, 4, 5, 6, 7. So it is a 3-bit asynchronous counter. 4-bit we can take one other another flip flop we can take. If it is a 4-bit one, is a 4-bit. Let us take this. A 4-bit means so truth table will be changes. So 4-bit means truth table will be changes. 4 flip flops are taken. So 4-bit means 4 flip flops. Let me draw here. It will be asked in examination. You can do the same thing. Okay, this is a 4-bit representation. So 4-bit flip flops are here. Again same thing, 4 flip flops. What is the changes here? Only flip flop changes. One more flip flop is added. Remaining all same. Remaining all same. Output as a clock. Output as a clock. Okay, output as a clock. Okay, this is JK. Right, this is JK. Q, Q complement. This is JK. Q, Q complement. So JK and Q complement. Q complement. JK. Right, Q and Q complement. Remaining all are same. Okay, two table will be 4. Okay, what happens? Two table will be 4. So Q naught, Q1, Q2, Q3. Okay, so it will be count from 0 to 15. Okay, 0 to 15. Likewise, you can take. Okay, so this is the first clock pulse is applied. First clock pulse is applied. Okay, then each output has a clock to the next stage. Each output has a clock to the next stage. So it is a 4-bit. This is a 4-bit counter. 4-bit asynchronous counter. Only one extra flip flop is added. Okay, remaining one more bit, one more counting Q0, Q1, Q2, Q3 flip flop is added. Okay, that is about 3-bit asynchronous counter. Each output has a clock to the next stage. Then first clock pulse is applied to the first flip-flop. Timing diagram, truth tables. Okay. Next, see the 3-bit 3-bit synchronous counter. Okay, 3-bit synchronous counter, right? 3-bit synchronous counter. Okay, 3-bit synchronous counter. Let's see the 3-bit synchronous counter used by 3 flip-flops. Simultaneous clock pulse is applied. JK flip-flop. Okay, see the designing part. This is the designing part of this one. Okay, 4-bit means one more flip-flop is increased. So nothing is there. Okay, like you can see. So this is the first JK flip-flop. Okay, J, K, Q0, Q0 complement, JK, Q1, Q1 complement, JK, Q2, Q2 complement. Okay, and you see there is a simultaneous clock is applied as we discussed in the differences between asynchronous synchronous. Okay, you can see this one now. Okay, and from here to we will take an AND gate here. So from here to here, one AND gate is there, the designing, one AND gate. So from here, she will be connected over here. She will be connected to this one. Okay, right? We will come on to the J and K. So first one it is high. First one it is high, or 5 volts. 5 volts it is connected. So clock pulse is applying. The clock pulse is applying. So as per that Q0, Q1, Q2 changes. AND gate is here. Okay. Anything? Okay. Let me go to the truth table. What is the truth table? Same. The clock pulse is applied. Clock pulse is applied. Q0, Q1, and Q2. Only designing part is different. So truth table and timing diagrams are same. Designing part is different one. So first clock pulse all are 0 0 0. Okay, 0 clock pulse. Initially it will be 0. First clock pulse is 0 0 1. Second clock pulse is 0 1 0. Third clock pulse is 0 1 1. Fourth clock pulse is 1 0 0. And fifth clock pulse is 1 0 1. Sixth clock pulse is 1 1 0. Seventh clock pulse is 1 1 1. This is what happened. As the clock pulse is applied, initially it will be 0. So first clock pulse is applied, then Q0 goes to 1. Then Q0 goes to 1. Whenever it will be 1, it will be toggle state. Change it to 1. Okay, and whenever the Q1 goes to 1, Q1 goes to 1 means before going to it will be 0. Before going to 0, first it sets this before going to 0, then it will goes to 1, then Q1 goes to 1, Q1 goes to 1, and again it will be 0, and Q2 will be no change state. Okay, this is what happened, right? And next, for the next count clock pulse, Q0 will be 1, Q1 will be 1, so Q2 will be no change state, and fourth one Q2 will be 1, so Q0 Q1 will be 1, Q0 Q1 will be 1, so 1 will be goes to here, 1 will be goes to here, and AND gate output will be 1. 1 is here, then Q1 is equal to 1. This is the fourth clock pulse is happened. The fourth clock pulse, Q2 will be 1. It sets the Q2, then it will be goes to the Q1, Q2 goes to the 0. Okay, let us see. Let me explain here only. So initial clock. So clock 0. So Q2, Q1, Q0. Q2, Q1, Q0, no change state, 0 0 0. Then second one. So clock 1 is applied. What happens? Q naught is equal to 1. Q naught is equal to 1. So Q1 toggle state. So Q naught is a toggle state. Change it to toggle. Means before it will be 0. Now it will be 1. Now Q1, Q2 0. No change state. Q1, Q2 0. Q1, Q2 equal to 0. It is no change state. Okay, we call it is no change state. Now third one. Third one. Clock 2 is applying. Clock 2 is applying. What happens? Clock 2 is applying. So clock 2 is applying. What happens? Before going to, so Q naught. So change it to 1 to 0. Change it to 1 to 0. It set it set it set the it set the Q1 1. It set the Q1 1. Okay, it set the Q1 1. Now fourth clock pulse. Fourth clock pulse. For the fourth clock pulse, what happens? So fourth clock pulse and third clock pulse. Third clock pulse, what happens? So Q naught, Q1 will be 1, Q2 will be 1, Q3 will be Q naught, Q1 and Q2. Q naught, Q1 and Q2. It is no change state. Okay, let me write here. The fourth one, clock 4 is applying. Clock 4 is applying. So before going to 0. So before going to 0. Before going to 0, so it it set Q1. It set Q1 is equal to 1. It set Q1 is equal to 1. So Q naught equal to Q1 equal to 1. Then AND gate high. Then AND gate equal to 1. AND gate equal to 1. Then what happens? Q2 is equal to 1. Then Q2 is equal to 1. Okay. Q2 is equal to 1. So this maybe happens. So this will be repeatedly, this will be continuously happen. This continuously happen. So continuously happen as per the clock. Continuously happen as per the clock. As per the clock signal. As per the clock signal. Okay. Right. So before going to 0, first it sets the Q2. It sets the Q2. So Q naught 1, Q1 1. So then Q2 will be 1. Q2 will be 1. So Q2, Q naught, Q2, Q1 and Q naught 0, 0 and 1. So it is a fourth clock pulse. So 1. Then it will be goes to 0. Then it will be goes to 0 means then it will comes down to 0. Okay, this is happened in fourth clock pulse. Fourth clock pulse. Right? Let me see the timing diagrams. Timing diagrams. Timing diagrams. Okay, timing diagrams. First, let us see the clock pulse. Okay, 1. So 0 to 7. Right? 0, 1, 2, 3, 4. Okay, 5, 6 and 7. Right? These are the clock pulses. Now, let me take this falling edge clock. Okay, the first one Q naught. Okay, as per this it will be changed. As per this each clock pulse it will be changed. Q naught. Now this is as a reference. Then Q2, Q1 also changed. Okay, Q1 also changed. As now previously we discussed the same timing diagram. Only difference is designing part is different. Only the designing part is different. Okay, let me see this one. 0, 1, 2, 3, 4, 5, 6 and 7. Okay, so this is Q naught, Q1 and Q2. So clock signal is applied. Clock signal is initially 0, 0, 0. Okay, 0, 0, 1. Okay, 0, 1, 0, 0, 1, 1. Okay, 1, 0, 0, 1, 0, 1. Okay, 1 1 0 and 1 1 1. The counting is so 0 1 2 3. This is 4, this is 5, this is 6, and this is 7. So this is the final count. Okay, this is the final count. So timing diagrams, truth table, and circuit diagram. These are the important. If it will be given 4-bit 4-bit means what happens? Only circuit level will be changed. Only circuit level will be changed. Timing diagrams and truth table will one more flip flop is added. One more flip flop is added. Let me here I'm drawing this diagram. Truth table, timing diagram you can practice, right? Truth table and timing diagram you can practice. So from here to here we'll take one AND gate. Okay, so after this these are connected over here again. So from here to you can take one AND gate here. Okay, so from here this is connected over here. Okay, again from this part you can take one more AND gate. Okay, again one AND gate over here. So each time AND gate is added. AND gate is added. J K. Okay, Q naught complement. This is J and K. So Q1 complement. J K. Okay, Q1 and Q1 complement. J K Q1 Q2. Okay, this is Q2 and this is Q3 complement. Okay, every time the AND gate is added. Okay, so from here to AND gate, from here to here, so from here to here, again this will be happen continuously. And the one more thing, the clock is here. The clock is simultaneous clock is applied. Simultaneous clock is applied. Okay, circuit diagram you can practice, and similarly timing diagram also same. Timing diagram also same. Okay, you can see this is a clock signal where you can take clock pulse is applied. Each clock pulse, then the outputs will be changed. So indicate 1, indicate 2, so it will be changed like. Okay, so this is about asynchronous and synchronous counters, right, which are used in digital frequency counter and digital clock, analog to digital converters, timing measurement. All digital displays are used in counters. Okay, please subscribe our channel. Okay, like and inform to your friends. Thank you.